So today we have a beautiful geometrical problem. It is one of the such problems that looks very simple and has a very simple solution, but the thinking process is little rigorous. You need to think a lot for the easiest and the best solution. Okay, so the details of the question is on the screen. You can take your time and read it. Okay, so now let us proceed to the solution. So the first thing, as you can see, we have arrangement of the sides of the triangle tangent to the circle. So why not utilize this particular theorem that says that tangents drawn to a circle from a same point are of equal length. So now look at the top point A. So from the point A, we have a tangent to the smaller circle over here, and also from the top point A, we have these two tangents of the equal length. So one with a very simple knowledge of lengths and arithmetic can make out if this length is having a length a and the complete length was b, so therefore the length from here to here will turn out to be b minus a. Okay, so instead of writing all this, I can just use the symbols of equal sides. So a dots over here means these two have the same length, and double dash means these two have the same length. Also, let us name these points as p, q, and over here let us name it as r and s. Okay, nice. Now, what I will do is I will draw a straight line joining P and Q and a straight line joining P and S. Remember that P, Q, R and S are the tangent points between the sides of the triangle and the circles. Okay. So now this kind of arrangement gave me an idea of this other theorem, that is the basic proportionality theorem. It says that if in any triangle the ratios are equal, then the sides are parallel. Not the sides, but the side dividing the ratio and the base would be equal. So in the similar pattern we have over here, as these two lengths are equal and over there this and this are equal and this are equal. So we can say that the dot length upon the double dash would be again the dot upon the double dash. I can just use the variable ABCD and it would be more clear, but as it is not required, I am not mentioning. So what is the conclusion fact from that? That this line would be parallel to this line. Okay, so I can just mention this thing over here, that we have concluded that PQ is parallel to RS. Okay, so now let us utilize the circles and the center of the circles basically. So if I assume that this is the center, I can draw the radius from R, let the center be O. So RO, OS, and this length over here. Okay, now you can just basically clearly see that this is the length x. The yellow line is just because the line is a straight line, but there is no length of that yellow line, or there is no task to even find that line. Okay, so these three would be the radius of the circle. And why not let us join this length over here. Okay, so now the diagram from the bottom is almost completed. Now let's move on the top. So if I assume the center to be over here, let me just thin. Okay, so if I assume the center to be over there, so this would be the radius, this would be the radius, similarly this would be the radius, and this would simply turn out to be a chord. Nice. Now moving back to the fact. Now before that, let's just be clear. Yes. Okay, wait, final try. Nice. Now let me just tell you, we are going to mark a lot of angle in this particular diagram, and for that let us use a bold color that you can see. Why not red? So now, as we were already having the fact that PQ is parallel to RS, if I mark this angle as equals to alpha, not the red color, it's not that much visible, let's use the yellow. Yes, so if I mark this angle as equals to alpha, by the alternate interior angle property, that is the Z pattern, the angle over here, the complete angle will turn out to be alpha. Okay, nice. Now the interesting part, if I mark this complete angle as equals to theta, what can you say about the angle over there? What if I tell you that that angle will also turn out to be theta? Now the question arises, how from here to there, how the angles are similar? So let us move back and learn a theorem over here. So okay, we need to again take, yes. So let's see this particular theorem. Not the theorem, it's just a basic geometrical what we say arrangement that gives rise to this kind of pattern. So suppose you have two lines, okay, that meet at a particular point P. Then you have a circle that is tangent to these two lines. Now you all know that if I draw the radius, this would be 90 degree at the tangent point, and if I draw a line joining P to that center, we have two congruent triangles, and if the two triangles are congruent, the remaining parts would become equal, and hence these two angles would be equal. So basically, because of this line PM, the PM has done a task and it has bisected angle P. Okay, now in the same figure, if I draw a bigger circle, wait, so in the same two line setup, if I draw a bigger circle that is also tangent to the both sides, Now what will happen? Again the radius would be drawn. Again a dotted line from P to the center of that particular circle, and let that be Pn. Now you can again see that these two triangles would be congruent, and hence the both angles at P would again be equal. So again the P has been bisected, but this time the Pn has bisected angle P. Now how come two different lines bisect the same? So the simple thing is that the two lines cannot be two lines, they have to be concurrent lines. So we can have this arrangement that the point P, the center of the first circle and the center of the second circle are in a straight line. This means that on the bigger line Pn, we already have that Pm lies on Pn. Okay, if it doesn't happen, then we will have two different lines, Pm different and Pn different, and two different lines bisecting the same angle is not looking a good thing to discuss. Okay, so we'll have these two lines are means it is a straight line. Now look carefully. As in this particular diagram you have seen above, we have marked this angle as equals to theta. Now recall that these two triangles were congruent, so the theta has been bisected into equal parts. So this would be theta by 2 and theta by 2. Now this over here is perpendiculars on the same base, hence they are parallel. So by corresponding angle, if that is theta by 2, this would be theta by 2, and this is theta by, means again these two are perpendiculars on the same base, so they are parallel. Hence by corresponding angles, this angle would be theta by 2. So the complete angle over here will turn out to be theta at the point M. The corresponding angle is basically simple. If there are two parallel lines and there is a line, then these two angles become equal, provided that these two lines are parallel. Okay. So yes, so now you have made out the idea why this angle is theta, then the top angle is also theta. Okay, nice. Now let's move back to the diagram. We are going to mark a bunch of angles. Okay, so just be patient and ready. So this is theta, that is theta. Nice. Now what further? Yes, the further thing is again a theorem. Now this theorem would this one is also a school theorem, it would be famous. I'm not writing the statement. It basically suggests the idea that from a common arc AM, the angle subtended by arc at the center is double the angle subtended by the arc at the circumference. Means if the arc AM, or sometimes some students say the chord AM, if it subtend an angle alpha at the circumference, then it will subtend an angle 2 alpha at the center. Okay, so let's utilize this theorem over here. Now look carefully. First of all, look at the arc AS, not AS, the arc RS. So it's not subtending an angle theta. Wait, yes. So now look carefully at the arc RS. So the first thing, don't make a mistake that is subtend an angle theta at the center. Instead, it is subtending this angle, and that is having a value 360 minus theta. Okay. So the central angle by RS is 360 minus theta. So the angle subtended by arc at the circumference is this one, and hence it would be half of the 360 minus theta. So this angle over here will turn out to be 180 minus theta by 2. Okay. Now look at Now look in this particular triangle, we have one of the angle as alpha, the other angle as 180 minus theta by 2. So by basic angle sum property, this angle will turn out to be theta by 2 minus alpha. Okay. Now this angle was theta. These two sides are equal because they are the radius of the same circle. The bottom two lengths would be equal, and by the bottom two angles would be equal, and by basic angle sum property, each of them will have the value 90 minus theta by 2, and over here also 90 minus theta by 2. Nice. Now recall that this point was a tangent point, this line is a radius, hence the point where the radius and the tangent meet is giving us a 90 degree. So the complete angle over here would be 90 degree, and for the similar reason the complete angle over here would also be 90 degree, and because of that same reason this was the radius, the thin line, so this would be 90 degree, and over here this would be 90 degree. This one is not required. Okay. Now look at each of these points. First of all, let us talk about the point R. So the complete angle is 90 degrees. Some part is 90 minus theta by 2. Some part is alpha. So the remaining part will have what kind of value? It will turn out to be theta by 2 minus alpha. Okay. Now over here, the complete angle is 90 degree. Some part is 90 minus theta by 2 and some part is theta by 2 minus alpha. So the remaining part will simply turn out to be alpha. Okay. Now over here we have a straight line. The part is 180 minus theta by 2. So the remaining part turns out to be theta by 2. Now over here, now the okay, so let me just be clear. For the bottom part we have marked all the angles that were required. Now moving on to the top part. So first of all, the arc PQ is subtending an angle theta at the center, and therefore it is going to subtend an angle theta by 2 at the circumference. Okay, nice. Now over here we have theta, so both of this would be equal because these two sides are equal radius of the same circle, and each of them will have a value 90 minus theta by 2. So let me just write it over here. This and this angle will have a value 90 minus theta by 2. Now look carefully, this complete angle was equals to alpha. Some part of it is 90 minus theta by 2, so we can have the remaining part, and it will turn out to be what? It will turn out to be alpha plus theta by 2 minus 90. Okay, now the complete part over here is a 90 degree. Some part is alpha plus theta by 2 minus 90, hence this remaining part over here will turn out to be 180 minus alpha minus theta by 2. Okay, nice. 180 minus alpha minus theta by 2. Okay, okay. Yes, now look carefully over here. As I told you, this angle would be 90 degree because radius and tangent points are meeting. Now what can you say about the complete angle over here? Complete angle, I mean from here to here. So this complete angle will have a nice value simply by adding 90 and 90 minus theta by 2. 90 and 90 minus theta by 2 will give us this angle is equals to 180 minus theta by 2. Now I hope I have marked all the angles in the above diagram also. Okay, so lots of angle has been marked. Now I give you a task that find similar triangle. So you may take your time and find the similar triangle. Now let me just introduce you to the similar triangles that I have figured out. So first of all, look at this triangle. The triangle. Okay, let's be over here. So look in the triangle. The triangle I'm talking about is triangle PQR. So this is the triangle that I'm talking about. Let me just draw it outside the diagram. So PQR. Wait. So the triangle PQR just looks like this. So we have P over here, Q over here, and R over here. The angle P for this particular triangle is 180 minus theta by 2. The value of angle R. What is the value of angle R? It's theta by 2 minus alpha, and the value of Q is simply alpha. Now I can see that this one is similar to this particular triangle over here. This point is missing. Let us just introduce as equals to E. Okay. So now look in this triangle, that is RES. Triangle RES. Okay. So this angle is equals to alpha. This angle is 180 minus theta by 2, and this one is theta by 2 minus alpha. So now you can clearly see that these two triangles have a very nice thing, that all the three angles are equal. So if any two triangle, all the three angles are equal, they become similar to each other. So I can write it down over here, and to write it down I have to use according to the correspondence. So the triangle PQR is going to be similar to triangle. Now look carefully, P is 180 minus theta by 2, so it should be equals to E. The angle Q is alpha, so it should be equals to R, and the angle R on that triangle is theta by 2 minus alpha, so it should be equals to S, ERS. Now once the triangle are similar by angle property, the corresponding part of the similar triangle become equal. So we will utilize the ratio. So PQ upon ER would be same as QR upon the RS, wait, QR upon RS, and that would be equals to PR upon ES. Now look in this particular diagram. Is the length PQ anything important? I don't think. The length ER, yes, ER is important because it is the X. So PQ upon X is equals to. What about QR? So QR is the complete length from the that complete line segment that was 2, the yellow length and the X. What about RS? Yes, it's something simple. What about PR? Yes, it is nice. Let's utilize that one, PR. And what about ES? ES is this particular side over here. So let us use that also. So I have just taken this two thing common and neglected the middle one. Okay, okay, nice. Let this be equation number 1. Now there's one more pair of instead there are many, but we have just figure out the other important pair of similar triangle. So now let me just draw that outside the diagram. So the first triangle is this one, PQ. The point is not in the diagram, I'll mark just now. This particular point over here, let it be F, where we have the angle theta by 2. So the angle P for now this particular triangle, what can you say about the angle P? Instead, let us focus on Q. So the angle Q is alpha, the angle F is theta by 2. So it is clear that this one is going to be 180 minus theta by 2 minus alpha. Okay. Now, after this, find a triangle that is similar to this one. So yes, one can easily find out. Let me just erase this. Yes. So one can now easily find out that this triangle over here is similar to this one. So let me just write down that triangle over here. So the triangle is simply EQS. Yes, the angle E is theta by 2. The angle Q is having a value of 180 minus theta by 2 minus alpha, and the angle S is having a value alpha. So one may notice that these two triangles become similar very nicely again by angle property. First of all, let us write down the first triangle PQF similar to triangle. Now look carefully. The angle P of this one is equals to the angle Q of the other. The angle Q of the first triangle is equals to angle S of the other, and similarly F of this triangle is equals to the E of the other, and they become similar by because of the angle property. Therefore, by CPST, one may say that PQ upon QS is equals to QF upon QF upon SE, and that is equals to PF upon QE. Okay. Now, do we have some important length? Let us see. So PQ, let it be PQ because we have seen in that equation number 1 we have kept PQ. What about QS? So let the QS be also stand by over there. What about QF? So look carefully, QF was having a length 2 that was already given in the question. Nice. What about SE? So we don't have anything, let it be SE, that is equals to. What about PF? So it is a journal length, and QE is also something general. Let us not utilize that thing. Just focus on this two. PQ upon QS is 2 upon SE. Now if I just write down these two theorems together, that PQ upon X is equals to PR upon ES, and now we have PQ upon QS is equals to 2 upon SE. What can one conclude? Or should I use PR upon ES? Okay, nice. QR and okay, let's see what happens. So now look, recall the fact that we have got this thing equal that let me just bold. Yes, recall the fact that we have got that PR was having the same length as equals to QS. These two lengths were equal because they were the subtraction of the equal tangents. Okay, so over here, wherever we have QS, I can just replace it with PR. So this QR I will just replace as PR. Okay, so now look in these two figures. What I can clearly see is PQ upon PR is equals to X upon ES. And from here what I have is PQ upon PR is equals to 2 upon SE, or I can say ES. So PQ upon PR, they both can be compared, and hence we will have X upon ES is equals to 2 upon ES. Look carefully, what is ES? It is a line over there. So it can just get cancelled out, and and hence we will have X is equals to 2. The value of X would be same as equals to 2. Okay, so lots of angle was marked in this diagram and just two bunch of similar triangles. The main thing was to keep patience and keep on marking the angles and have a nice observation to figure out the similar triangle and solve for the solution. So this was my way to solve this particular problem. If you have any other method, you can do comment below, and if it's a photo or PDF, you can email me. The email address is in the description. So these were the three easy geometrical problems, and I am planning to make shorts on this video regarding very simple geometrical problems, calculus problems, sequence and series, real analysis, group theory. Yes, I am planning to do lots of major math stuff on the shorts. Means just one simple question solved in seconds, and you enjoying while doomsday scroll, and you enjoying in between your doomsday scrolling of YouTube shorts. Okay, so nice. Thanks for watching this video. Bye bye.